Lecture 32 is our first lecture on dielectric properties of materials. In this lecture, we talk about a number of things related to the dielectric response of materials, such as dielectric constant, polarizability, polarization, depolarizing field, electronic susceptibility, and we talk about the Clausius-Massoudi equation to calculate the dielectric constant, and finally we talk about the first of two polarization mechanisms, electronic and ionic polarization. So first, you should be able to understand the relationship between different terms, new terminologies that we introduce here. First is the dielectric constant, which is also called the relative permittivity, which is related to the increase of capacitance when such dielectric material is inserted into a parallel plate capacitor. Remember, the capacitance is related to the amount of charge we need to put on these plates at a constant, at a particular voltage, potential difference that we need to set up between the two plates. This dielectric constant is related to the individual response of these atoms inside these materials. For example, when we have look at the center mass of the negative charge and the center mass of the positive charge, electrons versus nucleus, the relative location will be displaced when we have electric field applied. So the amount of displacement between these charges is so-called, will generate a so-called induced dipole, and this dipole moment will scale with the electric field we apply. And the scaling constant is so-called polarizability. If we have atoms that can be more easily polarized, that means the electrons can be more easily pushed away from the nucleus, then this atom will have a larger polarizability. We can also define this polarization vector, which is the total dipole moment per unit volume. So it's really the concentration of the dipoles multiplied by the average dipole moment per atom. And since the average dipole moment scale with the electric field, the overall polarization vector should also scale with the electric field, then defines a scaling constant, chi-e, which is the electric susceptibility, which is related to the dielectric constant in this simple form. Dielectric constant is 1 plus the electronic susceptibility. To understand the dielectric response, we should also look at the so-called depolarizing field. Because the material will be polarized, now we have a positive layer of charge and a negative layer of charge set up on opposite surfaces of this material. That sets up a so-called depolarizing field. That this depolarizing field, the magnitude of that depolarizing field scales with the polarization vector, but it's pointing in the opposite direction with the electric field or the polarization vector. And this depolarizing field effectively screens the external field that we apply, that we generate from the charges we have on the plates. And that set up a constant electric field inside, which is related to the eventual voltage we have, the potential difference that we have. So to maintain a constant voltage across the two plates, we need to, because of that dielectric response, now we need to put more charges on the plates to maintain a desired electric field. And that is the dielectric response of this material. So the second student learning outcome is to relate the microscopic polarizability to the macroscopic dielectric constant. There are two different situations. One is that to relate the microscopic polarization behavior of the atoms that's characterized by the polarizability, and then the macroscopic dielectric property is characterized by the dielectric constant. We have this very simple form in which the chi-e, the electronic susceptibility, is basically the concentration of the dipole moment of all these polarizable units multiplied by the polarizability of each divided by epsilon 0, which is the vacuum permittivity. This is a very simple form, but for systems where electronic or ionic polarization dominates, we actually need to apply a more accurate form to calculate the overall dielectric constant. That's because that the Lorentz local field, the local field is actually greater than the average field we have. And the correction term is related to the polarization vector of the in the system. So that means that the actual field we have, because the actual field is larger than the average field, that means the induced dipole moment per polarizable unit is actually going to be higher than what's predicted by the average field that we use to obtain the simple form of dielectric constant. So in this case, we have to apply the so-called Clausius-Massoudi equation to more accurately calculate the dielectric constant, which actually will be slightly greater than the result you would obtain from the simple form. So it is important to understand what kind of polarization mechanisms you have, because if there are multiple contributions, then you have to summarize all those different type of polarization mechanisms, the polarizability multiplied by the corresponding concentration. So this is the end of the review for this lecture.